This video will begin our discussion of integration using polar coordinates, a double integral turning into a polar coordinate. We do this to help us out. We've seen this in the past calculus classes that we can change coordinates and it actually will make some of our integrations much simpler. I'm going to drag you through very little theory on this, just barely through pictures. We could take some surface and we could project it down onto the xy axis. That's what we have here. Right, and we have that surface, and we have each region we can make these little rectangles that you can see over here. Instead of making the normal straight rectangular prisms like we did in the past, these will have a slight curve to them. Two sides will be straight, the other ones will have a curve that happens in rectangular. So what we need is we need to find the area of this thing. Well, this is going to be a bit tricky, but if it was a full circle, it would be pi r squared. But it's only a portion of our circle. So how we figure that out, and this is going to be weird, but this would be my area of my whole circle, but then I just want a portion of it, which means it's out of 2 pi, and I would just put my angle there. Right? That would take my angle out of 2 pi, that proportion of the whole circle, and find the area of it. Well, if I work that out, I get a 1/2. And then I get an r squared, and I have a theta. I'm putting the theta there because I'm going to match formula that you see below in a moment. So that's the area of a sector, given the whole thing. So it'd be like a whole slice of pizza, right? So if I wanted to figure out like one portion, like this portion, let's call this R2, and this R1, I could just take 1/2 R2 squared theta, and I would minus the small circle out, which would be R1 squared theta. They have the same theta, right? It's the angle's the same. You think about geometry there. And that would be my area of that piece. Now, we want to kind of limit a little more because we want to talk about our R's. So what we're going to do, instead of calling it R1 or R2, we can actually represent those by taking Ri, which is the point in the middle, directly in the middle of my sector. Oops, sorry for that. And if I take that Ri, let's call it Rk, and I add half the distance of R there, and I divide a half of it, that is my radius. This is equal to R2 or R1, depending. If I add it, I get this, I go this distance, and I get there. That's that outside. But if I subtract it, Rk minus change of R over 2, remember change of R is this distance. If I cut it in half, it's going to take me to that line, the inner. So this is the radius of the outside, right? This is the radius of the inside. Okay, just back like the other problems, if I can find the area of that little region, and I times that by the output of my surface, that gives me the volume of these weird rectangular prisms that are curved. If I add all those up, that gives me an approximation to the volume of that over those regions. So we can actually take that area, and I'm going to show that it's equal to this very quickly. I'm actually not even going to do the algebra side of it. This represents, using our logic above, I missed a little there, this represents the area of the outer sector. I know it looks a little different. This is our R2, right? And you can, that was that argument right here. And then change in theta is the same thing as our theta. We're just going to call them that because we have multiple thetas, multiple R's. If you do the algebra, and I'm going to leave that to you, that's up to you if you want to do it, you can get down to show that the area of sub k is Rk, that's the full R, times the change of R, that's in between, times our theta of that region. So I'm not going to show you how to get to that, but that's how we get to our formula that we're about to run into. Thus our volume is, okay, if this is the area of that region, and then normally we would have an f of xy, but in polar we don't call them x and y, we call them r cosine for x and r sine for that, so we would replace it all there. This represents a volume over the shape over that region. That doesn't help us a whole lot the way it stands because it's just an approximation, but if I take the limit with letting n go to infinity, the number of rectangles, we run into this. Okay, we get r cosine, r sine. That's what's going to be plugged in. That's just definition. And then we know from calculus, if I let things go to infinity with this stuff, those things go to 0, causing this like dr d theta thing. And then r just becomes r, giving us this new formula going from rectangular to polar. Here's the big kicker. Most people remember to do this. because they're like, okay, cool. All this means, let's write a note right here. Plug x equals r cosine and y r sine into surface. That's all that says. It's just, all that means is rewrite it in different terms. And it told you what x is and what y is by putting them in the same spot where x and y went. This is the part that everybody forgets, this r. The theory shows us why it shows up, but when we're working them out, what ends up happening is I have a lot of people, they'll convert to polar and then forget to introduce that r. What that r is called, it's called the Jacobian. This summer, because if you're in a summer section, we skip it. If you're in the regular semester, we actually do it in class. The only thing that's going to happen different if you're in my online section, you're going to watch that video, and we're not going to go over it in class. That may change in the future, so if I'm talking and this doesn't make any sense, it means I changed my mind and I'm still using these videos because I only re-record them every few years, because it takes a long time to make these. All right, that's our converting to polar. Let's go ahead and try an example. So we have this integral over region R, and then they tell me that R is a region in quadrant 1, bound by the circle x squared plus y squared equals 4. So notice I graphed the x squared plus y squared equals 4. You always want to graph. I'm very picky about my pictures, and I'm wanting them to look nice. So I've been doing them off camera. That way I can take my time. But the purple is the circle. They also told us y equals x, right? That's that red line. And then they also told me x equals 0, which means it tells me if it was here or where I have it. And it was below. If they would have told me y equals 0, then it would have been the one above. The only thing that keeps me outside of this other stuff, or right here I guess would fall into that, is that they told me it was in quadrant 1. So there is our region. This calls for polar, and the whole reason is that's circular. We can switch these to polar. I have x squared plus y squared now. I'm going to write these in here as a reminder. X squared plus y squared equals r squared. We also have x equals r cosine theta. And we have y equals r sine theta. Now I'm questioning if I wrote those down right. Yep, I did okay. There was one video in the past I wrote it down wrong, and it plagued me forever. Okay, so this circle, x squared plus y squared equals 4, ends up being r squared equals 4. Which tells me r is 2. Now, for my bounds, I like to write these before I start. I like to say r is between what, and theta is between what. I'm just going to set my bounds up. That way when I go to my integration, it's nice and straightforward. We always start at the origin because that's how r is defined. Let me grab another color here. We'll pop out there, blue maybe. R is if it's the region touches the point at the origin, the region does. We always start r at 0. So 0, and then we go out into the region, and whatever we reach first is the outer boundary, or like if it's variable, we'll have to change it. But in this case, r is 2 the whole time. Right? Theta, remember theta is an angle that starts here and spins outwards. So we just need to grab this angle. That's going to be theta. Well, that theta, if it's y equals x, that's a 45 degree. I'm not going to use 45. I'm going to use pi over 4, sorry. That's pi over 2, and it started at 0. So there are our bounds for r and theta. So now I just have to be careful to do the integral right. Okay, I do a double integral. I'm going to replace everything. X is r cosine theta. Y is r sine theta. And then this is the kicker, people skip this, r dr d theta. Right, our bounds, we always do r first in polar. The reason, because theta will not be variable. Theta will be in our problems that we're doing. We can make theta, we'd have to rethink everything, but theta is always going to be a constant. So I'm going to run r from 0 to 2. It didn't matter in this problem because r is not variable. Theta runs between 0 and pi over 4. And there's my integral. I just have to work it out now. Right, I'm going to factor out the 2. And I got theta equals 0 to pi over 4. Then I'm going to keep my r's. I'm just simplifying. That's all I'm going to do in this step. The 2 went outside. I got r cubed cosine theta. Sine theta. Let's replace that. Sine theta. Dr d theta. The r went with the other 2 r's to make the r cubed. All right, let's integrate that. I got theta is 0. Theta is pi over 4. All right, and we go up 1, divide by the new one. So this is 1/4 r to the 4th cosine theta, sine theta are just constants, so they just stick around. And I run r from 0 to 2, and then I still have d theta there at the end. I'm going to go ahead and factor out the 1/4, meaning I get a 1/2. And then I'm going to rewrite here. We're going to do a u sub. So the u sub here, let's plug our r's in actually first. That would be smart. Plugging our r's in, let's rewrite theta before we do any kind of subs. Plugging our r's in, the zeros are just going to go away. If I plug 2 squared in, I get 2 to the 4th, which is 16 cosine theta, sine theta, d theta. There we go. I'm going to factor the 16 out to give me an 8. This is going to call for the u sub here. So I'm going to let sine be u. That conveniently tells me that du is cosine d theta, which is going to get replaced right there, which is nice. Leaving me with the integral, okay, I'm going to have to replace my u's, of u du. It's really nice. All right, the u's, if sine of 0 is 0, we're just plugging them into here to get our new u's. Sine of pi over 4 is square root of 2 over 2. And then we have this nice little integral here. I got 8 of 1/2 u squared from u equals 0 to u equals radical 2 over 2. The 0 is just going to 0 out. That's great. Then I got 8 times 1/2 times the square root of 2 over 2 squared. So we get 4 times 2 over 4. That's a half times 4, which gets me a nice pretty 2. So the volume of that shape, the surface above that, whatever that surface may produce on top of that little pink sector, the volume of that thing would be a 2.